All right, Gen Chem 2 class. This is the recording for the 1st of March, 2021. The announcements. We are now into chapter 16. We finished thermodynamics. The lab is coming up on this week, Tuesday and Thursday, and these are the due dates for Alex. So chapter 16, equilibrium, the topics are split in half. Actually, there are a couple of topics that we're going to come back to later in the semester. But 16A and 16B, we'll have today and Wednesday to go through the first part. We'll finish up equilibrium on Friday. All right, let's see, worksheets. So for those of you in the online class, these are the due dates for worksheets 11 and 12. And don't forget, we have an exam coming up next week, Tuesday and Wednesday. Well, we have to have a little bit of despair. Turn the lights here. There we go. That might help with viewing some of the rest of the slides later too. Okay, so let's start with, because a friend in need is a friend I don't need. The science of explaining tomorrow why the predictions you made yesterday didn't come true today. Hard work never killed anybody, but it is illegal in some places. Yeah, they have a 30-hour work week in France. It's lonely at the top, but it's comforting to look down upon everyone at the bottom. Failure is just the opportunity to begin again more intelligently. And if you're surrounded by screw-ups, you'll become an expert in it. Unless you try to do something beyond what you've already mastered, you'll never fail. And if you keep asking others to give you the benefit of the doubt, they'll eventually start to doubt your benefit. Okay. Now that we're suitably encouraged, let's head on to chapter 16, equilibrium. We've already talked about equilibrium in a couple of different contexts. Excuse me. We've talked about equilibrium in terms of reaction mechanisms for kinetics, where we have that fast equilibrium in the first step. The rate forward equals the rate reverse. And we already also talked about equilibrium in terms of free energy. Delta G is equal to minus RT natural log of K. Now we're getting to the equilibrium constant. And in the equilibrium constant, we have a given reaction, reactants, coefficient, thing, coefficient, thing, and then we form the two products with their own coefficients. The equilibrium constant is called K, capital K, the equilibrium constant. The equilibrium constant expression looks like this. It's where we take the products raised to their coefficients divided by the reactants raised to their coefficients. The equilibrium constant expression always follows the same pattern. Now, we already talked a little bit about equilibrium on Friday in terms of the fact that how you express K and how you express Q. So I'm not going to go over that too much further, other than to say those two terms, equilibrium constant represents K, and there are lots of different forms of K, and we'll have a little subscript by it. This is called the equilibrium constant expression. Equilibrium, you have the double arrows. If a system is at equilibrium, the rate forward equals the rate reverse. So let's write equilibrium constant expressions for these. Can we do that? We'll just see what's on the next slide. Yeah, let's go back. Let's take a look and see what it means to write equilibrium constant expressions for some of these. As I already talked about to a very brief extent, you never include solids or liquids in an equilibrium constant expression. So we've got solid, liquid, gas, and AQ. In an equilibrium constant expression, anything that's solid, anything that's liquid will never appear. And the reason is because their concentrations don't change. Their concentrations are constant. Those constant concentrations get rolled into the value of K. The only concentrations that do change are gas and aqueous solutions. Okay, so for this first one, how would we write the equilibrium constant expression? Let me move this over here. K is equal to the way you would begin any equilibrium constant expression. The products and the coefficient is 2, so that becomes squared. Notice that this is not a rate constant, this is an equilibrium constant. If these were rate constants, then we can't necessarily put coefficients as exponents. But for equilibrium constants, we do. All over to SO3, that's a gas. And it looks like this. That's how we would write the equilibrium constant expression. If we take this reaction and reverse it, which is what the second reaction is, what we have here as products now become the reactants. How does that affect K? Well, this becomes SO3 squared in the numerator, SO2 squared times oxygen to the first in the denominator. In other words, it's this expression flipped. It is 1 over. So if we reverse a chemical reaction that's at equilibrium like this, if we write it in reverse, K, the previous K is now 1 over K. For this one, K is equal to H plus and OH. Those are aqueous ions. I didn't put AQ here. But if you see ions, they are automatically aqueous. They're automatically dissolved in water. Coefficients are both 1. Divided by water. But this is a liquid, so it does not appear. For something like this, sodium hydrogen carbonate, you know how to name that, right? Sodium bicarbonate or sodium hydrogen carbonate, according to the official name, goes to CO2 and NaOH. K here is equal to, we don't include this because it's a solid, we do include CO2. Coefficient is 1. Divided by this, but this is a solid, so it doesn't appear. This is all there is to the equilibrium constant expression for this reaction. And finally, CO2 plus NaOH goes to sodium bicarbonate. If we take this and flip it, well, K is simply 1 over CO2. Writing equilibrium constant expressions. Writing equilibrium constant expressions. So that's about all there is to it. I'm not sure if that's going to work. The light's off. I don't know if you can see all of this stuff. So doing a little experiment here with lighting. Hope this comes through on the Zoom. Okay, how do you feel about that? Can you write equilibrium constant expressions on your own? Excellent. Next, we come to Le Chatelier's principle. Keep in mind what we have in equilibrium. We start with reactants, and move over and form products. They start to form more and more and more products. Then the products start to go back to where they came from. Now you begin to have a buildup of product that now begins to go back to reactants. You will eventually reach a point where for every set of reactants going to product, you have product going to reactants. And when the rates are the same, then you have equilibrium. Equilibrium is a state of balance. Here's Le Chatelier's principle. So think about this. We have an equilibrium, the state of balance. Products, reactants. They're maintaining their same concentration. They're still dynamic, they're still moving, but they're at the constant concentrations. Now let's say we affect that equilibrium somehow. There are 3 ways we can do that. Any kind of a stress placed on it means that that equilibrium can shift left or right in order to relieve the stress on that equilibrium. And here are some examples of how that happens. First, concentration. Let's say we have reactants, products. If we have a system in equilibrium. If we dump some more of one of our reactants in, that is going to shift the equilibrium. The equilibrium will shift to relieve the stress of adding one of the components to the reactants, and it will shift to the right. So the system will shift away from the added component in order to reattain equilibrium. Temperature. If we change the temperature of the equilibrium of the reaction, the equilibrium will shift. We'll give you an example of how that changes. And then, so let's take a look at this. I don't know how well you can see the reaction in red here. H2O gas, CO gas, carbon monoxide goes to H2 gas plus CO2 gas. Excuse me. In this particular reaction, water is giving an oxygen to carbon monoxide. Okay, so what if we have the system at equilibrium and now we add hydrogen to it? We have this beautiful state of balance, and now to that state of balance we increase this. If we increase this, it's no longer balanced. The reaction shifts to the left, excuse me. The reaction will shift from right to left until equilibrium is reestablished. If we go back to our equilibrium that we started with, and if we take carbon dioxide and pull it out of the system, if we pull this out of the system, the equilibrium shifts right until equilibrium gets reestablished, that state of balance. So remember the concentrations. Excuse me, let's take a look at this one. So keep in mind that K is a constant value. So what happens if we have this nice balanced system where the numerator divided by the denominator is equal to K? So a nice state of balance. Now, we increase this. If we increase this, K doesn't hold anymore. So what happens? If we increase this, the reaction shifts left, using up some of this, increasing some of this, until we hit K again, until this proportion is equal to K. So what happens here? If we increase hydrogen ion concentration for this reaction, this was that water goes to H plus and OH. What happens if we increase this concentration? Well, we're no longer at equilibrium. If these are already balanced, we increase this, the reaction shifts left until K gets reestablished. If this goes up, then this will have to go down to reach equilibrium. If we take some of this away, then this will have to increase until we reach K again. It's all about the state of balance. K is a constant value for any reaction at a given temperature. This is what happens when I talk too much. The third one is pressure. If we have a system at equilibrium, and let's say we put an inert gas in there, like argon. They fill light bulbs with argon, an inert gas. An inert gas does nothing to affect the position of the equilibrium. But if we take our system at equilibrium and we compress the volume, usually that means increasing the pressure. If we compress the volume of our closed equilibrium system, now what that's going to do is favor the side with fewer number of gas phase moles. We already talked about this in terms of entropy. Entropy can either decrease or increase depending upon the number of gas phase moles on a given side. It's a little bit similar to that here in terms of equilibrium. Okay. So let's take a look at this particular problem now. The nice thing about equilibrium is that it's quantitative, or for some of you that may not be such a nice thing. Anyway, let's take a look at what we have here. So, by the way, on the worksheet, you'll find that how does an equilibrium shift if you add or subtract things, put things in or take things out? You can actually take a look at the worksheet and walk through it and decide. I feel like I'm missing a slide here, but so let me pause and go back. Actually, I'm not really going to go back. I want to expand upon this. I'm going to work over here and use a different reaction just to give an example. Let's look at this reaction. It's an equilibrium. Everything is in the gas phase. You know that hydrogen and oxygen are 2 of the 7 diatomic elements. You should know the other 5. 2 of the 7 diatomic elements, gas phase. So let's say that delta H for this reaction is equal to delta H for this reaction. I'm going to make up a number. It's around 240 kilojoules. No. I have a feeling it's on the order. Let's say 40. Now, again, I'm making up this number. This number is quite negative. This plus this wants to go to the right. Given this information, let's just review what we've already done with regard to Le Chatelier's principle in affecting concentration, in terms of affecting temperature, and in terms of affecting pressure. So let's take a quick look at how that would work. We've talked about concentration. So we have a system everything's gas phase. Write the equilibrium constant expression. Here's K, equilibrium constant expression. Our system's at equilibrium. What happens if we increase the hydrogen gas concentration, not ion, hydrogen gas? If this goes up, which way does that shift the equilibrium, if at all? If this goes up, it has to shift the equilibrium to the right. To relieve the pressure of adding more of this, it's going to go to the right until the state of balance is re-achieved, until the concentration of water vapor over hydrogen and oxygen achieves K again, achieves that proportion. If we're at equilibrium, and now we increase this has got to shift along with some oxygen into this until K gets reestablished. That happens if we take hydrogen away. If we take hydrogen away, the reaction shifts left to make more of it until K is achieved again. We can choose any component, any reactant, any product. We can increase water. If we increase water vapor, shifts it to the left. If we pull water vapor out, shifts this equilibrium to the right. In terms of temperature, what about this reaction? Given this reaction, we see delta H. Is this reaction endothermic or exothermic? Endothermic or exothermic? Delta H is negative. All we need to know is if delta H is negative or positive. Delta H is negative, the reaction is exothermic. This reaction produces heat when it goes. In other words, let's just include heat as a term. Heat does not factor into the equilibrium constant expression, other than the fact that we know that K is a constant at a given temperature. So now, let's say that we change the temperature. If we change the temperature, remember that heat is considered a product. It's exothermic. Every reaction is exothermic or endothermic. There's always a delta H because we have reorganization of bonds. Bonds broken, bonds formed, there's always some change in bond energies. That is where the enthalpy comes from. So let's take this reaction, and if we lower the temperature, let's say it's at room temperature, and now we cool it down. If we cool it down, what are we doing? If we're cooling it down, we're removing heat from this. We're pulling the heat out of the reaction. That's going to drive this reaction to the right. We think of heat as one of the components. If it's exothermic, heat is a product. If it's endothermic, we have to put heat into that, and heat would be a reactant. In this case, delta H is negative, heat is a product. If we cool this reaction down, the reaction shifts right to make more heat. If we take this at room temperature and now we heat it up, if we heat it up, we increase the heat, that drives this reaction to the left. That's how you think of how equilibrium shifts when you change the temperature. Now, the last step, pressure. What do we do with pressure? So let's take this reaction, which is at equilibrium, and let's change the pressure of the system. In other words, let's take the system, and let's say that we compress it. We put more pressure on it. We take the same components and we squeeze it down. If we increase the pressure, remember everything's a gas. 2 moles of gas plus 1 mole of gas gives 2 moles of gas. 3 moles of gas on the left, 2 moles of gas on the right. If we increase the pressure, the reaction shifts toward the side with fewer numbers of gas phase moles. So if we increase the pressure, the reaction is going to shift to the right. Instead of having 3 gas phase moles, we would rather shift to the side with 2. The reverse is true. Let's say we take the system and expand it. We lower the pressure. If we lower the pressure of the system, then the reaction will shift toward the side with a greater number of gas phase moles. That is how we apply Le Chatelier's principle to a given reaction. For concentration, you're either increasing or decreasing one of the components. For temperature, consider where the heat term is. It's either a product if it's exothermic or a reactant if it's endothermic. Raising or lowering the temperature is like changing the heat term. And then finally, for pressure, look at a reaction, numbers of gas phase moles. So let me just refer to this slide one more time. If we go back to this slide, we can apply those 3 principles to any of these 5 reactions. Increasing the concentration of a gas phase component, remember solids and liquids, doesn't matter if we increase a solid or a liquid. All that matters is that some of this is there. If none of this is there, that's a problem. As long as something's here, concentration is irrelevant. In order to get temperature information, you would have to look at delta H for each of these reactions. Okay, so let's get back to where we were. Yes. Okay, now let's take a look at this problem. This is the chemical reaction we are going to do in lab, not this week, but next week. This is not the thermodynamics lab. This is the equilibrium lab. So this will be the lab for the week before spring break. We have a relatively simple reaction here. Notice that all of our coefficients are 1. Everything is ionic. In other words, these 3 ions are all aqueous. Here's the issue. We start with 0.15 molar iron, 0.15 molar thiocyanate. They're mixed. At equilibrium, we have this. What is the value of the equilibrium constant? This is a typical equilibrium type of calculation. And this is where we're going with this today. I think this might be, I'm not sure, it might be all we talk about today, but we'll see how I'm feeling in a few minutes. If I feel like, hey, we got a lot more to talk about, we'll keep going. So let's take a look at how we approach problems like this. The real key here is when you look at a problem for equilibrium, what are you starting with and what do you have at equilibrium? Because when you start with stuff, you're not at equilibrium. Usually you're just starting with one or two things and that's it. The reaction happens, you reach equilibrium, and then now you can calculate the equilibrium concentrations, or you can calculate or you can calculate K. Knowing K is a big deal, the value of the equilibrium constant. So here we're trying to find the value of the equilibrium constant. And this is how we set this up. So we take the reaction. We have the reaction. There are three lines that we come up with. And this is called an ice table. Some people call it a rice table. They include the reaction. I'm calling it an ice table because that's what I prefer. So you take the reaction, and here's what we have. What are we given initially? We're starting with these two things. We're starting with Fe, 3+, and thiocyanate. That's what the problem in the previous slide told us. And if you don't believe me, go back and make a note. This is what we have. This slide is simply taking the data that you were given in the problem and organizing it into a table. How much of this did we start with? We were told we weren't given any information about it, so that must be 0. What happens? These two things react. They go to the right to form this. How far does it go? We're not sure yet. What we're told, however, is that at equilibrium, this concentration is 0.1. The only three things we were given in the problem were this, this, and this. So from the problem, we can infer that this starting amount was 0. And we end up with 0.1. Now, for every equilibrium problem, when we're looking at shifts, this is how you do it. You do the ice table. What are the initial concentrations of each of our components? What change happens? And what do we have at equilibrium? Let me just check my next slide here. Okay, so let's go ahead and work this through. So we have the reaction. Always start with the reaction, and then underneath each of the components, you write whatever concentrations you know. If you don't know what something is, just leave it blank. So here's the key about ice tables. Initial, change, equilibrium. So you see where the ice comes from. The I, the C, and the E. The initial plus the change equals equilibrium. So these two added together give us this. These two added together give us this. Initial plus change equals equilibrium. This plus this equals this. This plus this equals this. This plus this equals this. So what was the change that occurred for the FeSEm? The sum of these two is equal to this. This is clearly plus 0.100. It went from 0 to 1, 0 to 0.1. Here's one other tip I would urge you to do for any of these problems. For the change, always use plus or minus. Always use plus or minus. Because the change is either something gaining concentration or something losing concentration. In this particular case, notice what we're given this and this. That's 0. There was nothing there. We know that the reaction goes from left to right. It has to. There's nothing over here to shift from right to left at the beginning. So from the beginning, we're only given these two concentrations. It has to shift to the right. In other words, we are forming products. So the change goes from 0. And here we're told the equilibrium concentration is 0.1. So we know that change. Okay, how are you doing so far? You see how we set this table up? You see how we got this plus 0.1? Remember to use for the change always plus or minus 0.1. Here's the next step. Whatever the change is, whatever this change is, it is stoichiometric. It is stoichiometric. In other words, 1 to 1 to 1. All of our proportions are 1 to 1 to 1. So whatever this gains, this is losing. If we lose 1 mole of this, we gain 1 mole of this. If we lose 1 mole of this, we also lose 1 mole of this because of the relationships. Now, this isn't the case, but let's say, I'm going to make stuff up. Let's say that for a moment, that this were 2 and this was 3. If that were the case, our change would be whatever we lose here, this was losing twice as much. And this is gaining 3 times that. This is only for the change line. If these are the coefficients, this is the change that happens if we're going from left to right. We're losing this, we're gaining this. If that's our stoichiometry. If that's not our stoichiometry, it's all 1 to 1 to 1. So what we do is whatever we lose here, we lose the exact same amount here, and we gain the exact same amount here. In other words, for this particular problem, we know what x is. We know what the change is. The change is 0.1. So we are losing 0.100 from each of our reactants. And we know this because if this is the amount that this gained, we lose that exact amount here. It is only the change line where we use the stoichiometry. Now, remember this plus this equals this. At equilibrium, we have these numbers. Because we know the change in one thing, we know the change in everything. We now know the equilibrium concentrations of everything. And if we know the equilibrium concentrations of everything, we can find K. Because we know how to write equilibrium constant expressions. And for this reaction, it's equal to FeSCN 2 plus all over Fe3 plus SCN minus at equilibrium. At equilibrium, now we plug in our numbers. That is 0.100 molar all over 0.5 times 0.5. 0.05. 0.1 over 0.05 squared. So you take this and you divide it here. I think you get 4. 0.1 divided by 0.05 is 2. 2 divided by 0.05 is, it's not 4. Okay, I'm going to do the calculation. Let's see, what is it? 0.1. 40. 40. K is equal to 40. We typically do not use units for K. Typically do not use units for K. The value of K. All right. I think what we'll do is stop here for today and focus on worksheet number 11.